Okay, so for problem number one, 10% hydrogen means you have 10 grams of hydrogen, and it's a hydrocarbon, so the rest is 90 grams of carbon. So the first thing you're going to do is convert this to moles. So 1 gram of hydrogen per every 1 mole. That's going to be 10 moles of hydrogen. The next thing you're going to do is convert that to moles of carbon. So 12 grams per every 1 mole of carbon. Okay. You're going to go through this process and you're going to end up with, I believe, this is going to be, let's get a calculator out here. So what's 90 divided by 12? 90 divided by 12 is 7.5. So you're going to end up here with 7.5 moles of carbon. So you're going to divide this by 7.5, and you're going to divide this by 7.5, and you're going to end up with 1 here, and you're going to end up with 1.33 here. So you can multiply that by 3 and get pho, and multiply that by 3 and get 3. So those two together will give you C3H4, which is the answer to number 1. When water boils, remember that you're just breaking the intermolecular forces. The bubbles in water vapor are just, or the bubbles in boiling water are just vaporous water. So there's the hydrogen bond there, and that's the only thing that breaks. We do not break the covalent bonds. So that's why the answer here to number 2 is B. Okay, remember the relationship here. So as you increase the boiling point, you're going to decrease the vapor pressure. But also remember that if we plot the IMF forces versus the boiling point, they're going to be directly related. So as the IMF forces increase, so does the boiling point. As the IMF forces increase, the vapor pressure decreases. So we could have this relationship here, like that. So it says which of them has the weakest intermolecular forces? That would be the one with the highest vapor pressure. So in that case, it's C3OH, and the answer is C. Number 4. First off, when you look at this, you know it's a little strange. This is not drawn to scale. This should really be drawn this way. And what makes the molecular geometry of this different? Well, that's the lone pair on the central atom. Okay, so that's why the answer to this one is D. S has an additional lone pair of electrons surrounding its C. I know that C is a little tempting, but the lone pairs of electrons don't make the S the negative end of the dipole. Actually, that arrow is pointing towards O. O is the negative end of the dipole in this case. Answer being D. Immediately, when you see a drawing like this, you should think about polarizability. So they say that the difference in boiling point between Br and I2 is 59 to 184 respectively, and they ask why. Well, since they're both nonpolar, they both only have London dispersion intermolecular forces. So the only thing that could account for the difference in boiling point is a difference in London dispersion forces. And we know that that difference is always controlled by polarizability. Okay, so we're going to look for that word. There's the word right there. And does it make sense? Yep, I2 molecules have electron clouds that are more polarizable. If we were to draw this in a conceptual fashion, it would be something like this. You know, these electron clouds in iodine, just like big bubbles, can wander more, making them more polarizable and making those London dispersion forces stronger. In this case, whenever you're heating something to remove another substance, you always need to heat it to constant mass. When the mass stabilizes, that means you've removed all of the substance. Okay. In this case, this is another empirical formula problem. We have 3.21 grams of sulfur, and you have 11.4 grams of fluorine. So you're going to divide this by the molar mass of sulfur, which I believe is around 32 grams per every 1 mole. And we're going to end up with 0.10 grams of sulfur. And you're going to divide that by the molar mass of fluorine, which I believe is around 19 grams. So I'm going to go up here and I'm going to say 11.4 divided by 19 What did that say? 11.4 divided by 19. And that's going to be 0.6, and I already can tell what the answer is going to be. 0.60 grams of fluorine. I'm going to divide them both by the smallest and end up with D, SF6. Which of the following is nonpolar but has polar covalent bonds? So let's go ahead and draw them all out. A, B, C, and D. So the Lewis structure for A should look like this. That's polar. B should be a T-shaped molecule, and that's going to be polar. C should be a square planar molecule. That's going to be nonpolar. And D should be a tetrahedral molecule. And that's going to be polar because of the difference here. So the only even molecule that's nonpolar is this. A lot of people have been struggling with this class or this problem. That's a polar bond, okay? Xe pulls harder than H. But all those polar bonds cancel out to create an overall nonpolar molecule. Okay, we want gases to expand. And gases are going to expand when they have a really high temperature. So it's going to be one of these two. And they're going to expand when the environment is not pressurizing them. So that's why the answer to this is going to be C. And 10. 3 gases are shown. What's the partial pressure of CH4? So initially, we're going to try and do PV equals nRT here, but we realize we don't have enough information. We don't have the volume. So in this case, we're going to do a partial pressure calculation, which is going to say that the partial pressure of CH4 is going to be equal to the moles of CH4 divided by the total moles multiplied by the total pressure. So let's go and plug that in. That's going to be 0.90 divided by 1.5. That's the total moles because 0.9 plus 0.35 plus 0.25 is going to be 1.5 multiplied by 3.0, giving us the answer is C, 1.8. Let's go through the free response questions here. So we got this reaction right here, and they say you have 20 grams of NaN3. The first thing I have to do is convert that to moles. So 65 grams per every 1 mole of NaN3. But we want to get the volume of nitrogen gas. So I got to use the mole ratio. 6 moles of NaN3 per every 9 moles of N2 gas. This is going to give me N, or moles of N2. I'm then going to pump that in and say that V equals nRT divided by P, and I got the P here. I add that to 273, I got the T. I know that R is 0.0821, and I got my answer here, and it's going to be 12 liters of N2, and that's the size of a car airbag. Do you predict the pressure inside the airbag to be higher or lower if the pressure inside has increased? Okay, and that's going to be higher. We say it's a constant volume. So I'm just going to speak this answer. There's 2 ways of doing it. At a constant volume, as temperature increases, so does pressure. Or we can say, as the temperature inside the airbag increases, the kinetic energy of the particles also increase. And if the kinetic energy of the particles also increase, they're going to hit the walls of that airbag that has a constant volume with greater force, thus increasing the pressure inside the airbag. Nitrogen is great for airbags. There's the Lewis structure for nitrogen. And partly because it is nonpolar. If it's nonpolar, it means that molecule has really, really, really weak intermolecular forces. It only has London dispersion intermolecular forces. It also means that it's small. And because it's small, its London dispersion forces are weak due to the low polarizability of the molecule. So it really, really wants to expand. Okay. Azide. Let's look at the Lewis structure for azide. When you do it all out, you're going to end up with this. If you calculate the formal charge, let's call this N1, this N2, this N3. So N1 equals -1, N2 equals +1, and then 3 equals -1. Remember that formal charge is found by taking the valence electrons or the owned electrons and subtracting it, oh no, the valence electrons and subtracting it from the owned electrons. Let's do N2 as a case study. So the valence electrons for N2, N is always 5. And the owned electrons, we know that this counts as 1 and this counts as 2 because really they're sharing 2 here, so they really only own 1. So that's equal to +1. And that's where that came from. Okay, based on your formal charge, does it lend insight into it? Well, in order for this reaction to really happen, this N3 has to decompose into N2. And it's going to decompose if it doesn't like being the way it is. And in this case, we don't have any element, specifically the central atom, does not have a formal charge of 0. So it's a very unstable element and very prone to forming N2 and really filling that airbag. Let's look at problem number 2. In the space below, draw the photoelectron spectra for sodium. Okay, so we know that this is the number of electrons, and this is energy. We can say ionization energy. I'm going to call this high, and I'm going to call this low. We know that sodium is 1s2, 2s2, 2p6, 3s1. So there's my 1s2 peak. There's my 2s2 peak. There's my 2p6 peak. And there's my 3s1 peak. Okay. Although not as reactive, they are asking us to draw magnesium on the same scale. So we know that magnesium is directly to the right of sodium on the periodic table. Well, magnesium is going to have a higher ionization energy because although they both have electrons in the third energy level, 2, 3, sodium has 11 protons pulling on those 3 levels, but magnesium has 12 protons pulling on those 3 levels. So magnesium is pulling with a greater force, meaning all the electrons are harder to remove. So magnesium is going to be shifted over here, 1s2, 2s2, 2p6, and magnesium is going to be 3s2. Let's draw it here so you can see it. 1s2, 2s2, 2p6, 3s2. Okay. They want us to show NaCl dissolving in water. Okay, so we know that NaCl, when it dissolves in water, is going to break into an ionic compound. And we know that the water molecules are going to surround it. And I'm drawing it this way because this is the partially negative and this is the partially positive. And this is the partially positive. And it's going to be the opposite on this side because of Coulomb's law. Now this is governed by Coulomb's law. So even if this is a partial charge to a full charge, the larger that partial charge and the larger that full charge, the stronger the attraction. Also, the smaller this ion and the smaller this ion, the greater the attraction. Remember that Coulomb's law says that the force of attraction is equal to the charge value divided by the size. So because that's a positive and that's a negative, the smaller they are, the stronger they are attracted. The greater the charge, the stronger they are attracted. Let's go on to number 3. Which acid has a lower vapor pressure, HCl or HBr? So with these, I'm just going to speak them out. I'm going to write out a little something about both of them, and then I'm going to speak out the answer. Okay. So both of these molecules are polar, so they both have London dispersion and dipole-dipole, and London dispersion and dipole-dipole. Neither of them have hydrogen bonding. So hydrogen bonding is going to be what strengthens the dipole-dipole. Neither of them have them. So it's got to be a London dispersion force. Okay. So because they're both polar, but neither has hydrogen bonding, HBr has a lower vapor pressure because Br is larger than Cl. Thus, HBr is a more polarizable molecule, yielding a higher boiling point and a lower vapor pressure. Okay. Is the atomic radius of Kr higher or lower or the same as Ar? Now I believe Kr is lower on the periodic table. So Kr has a larger atomic radius because Kr's electrons are more shielded from the nucleus, thus yielding a lower ionization energy and a higher atomic radius. Who has a higher melting point, NAF or MgO? So I'm going to draw this one out. You have NAF and you have MgO. Now, they're both ionic. So this is really Na plus and F minus, and Mg2 plus and O2 minus. Now remember, they're ionic because Na is a metal and F is a nonmetal. And Mg is a metal and O is a nonmetal. So because Na and Mg are in the same row of the periodic table, they're right next to each other, they have relatively the same size. And because F and O are in the same row of the periodic table right next to each other, they have relatively the same size. But because the ions of Mg and O2 are larger, there's a stronger attraction of this lattice, thus yielding a higher melting point. Which species has a lower boiling point? Let's draw the Lewis structure for these. There's NaH, and there's Na. Sometimes I like to circle the lone pairs. Okay, so let's over here write a little key. They're both polar, so they both have London dispersion and dipole-dipole, and they both have London dispersion and dipole-dipole. So we know that London dispersion is strengthened by polarizability, and dipole-dipole is strengthened by hydrogen bonding. London dispersion is strengthened by polarizability, and dipole-dipole is strengthened by hydrogen bonding. We see that in NH3 there is hydrogen bonding, or the potential of having hydrogen bonding, because of the large dipole created with the NH bond. Therefore, this thing does have hydrogen bonding. Therefore, NH3 has a higher boiling point. Thus, the molecule with a lower boiling point is NCl3. Okay. If we draw the Lewis structure for SO2, it's going to look like this. And if we draw the Lewis structure for SO4 2 minus, I'm assuming you all can do that, it's going to look like this. So in order to talk about bond length, we need to get the bond order for each of these. So bond order is found by taking the number of bonds, 1, 2, 3, and dividing it by the number of external atoms. So that's 1.5 here. The number of bonds here, we'll call it BO, 1, 2, 3, 4, dividing it by the number of external atoms, 1, 2, 3, 4. So the SO bond length is longer in SO42 because the bond order is smaller. It's also weaker. So if you look at strength of the bond and bond order, those are going to be directly related to each other. But if you look at length of the bond and bond order, those are going to be inversely related to one another. Using the colorimeter, a student measures the absorbance below. What is the absorbance or concentration at an absorbance of 0.25? So if we go over and come down, it's relatively about 0.05 molar. Okay. All right, so this is Beer's law. So a sample is equal to what it is, that's epsilon, multiplied by how long or the path length the light has to travel, multiplied by the molarity. So if you have something in a sample and light is passing through, and some is going to be reflected and some is going to be absorbed, the distance that that light has to travel is called L. What the sample is epsilon, and how far, or the concentration of the solution is C. In this case, if they leave their fingerprints on it, okay, it's going to increase the absorbance. The fingerprints are going to cause more light to be absorbed and less to be reflected. But because we're not actually changing the concentration, nor the path length, nor epsilon, it's going to give a false value for the absorbance. This is not good for calculating the absorbance of something like sodium chloride because absorbance depends on some light actually being absorbed. And we know that only transition metal ionic compounds, like ionic compounds that contain copper or cobalt or silver or lead, or, I mean, those aren't good examples, like manganese or cadmium or things like that, chromium, those are things that are very colored. And we would use a different method for calculating the concentration of something like NaCl that was not colored. In this case, they want you to calculate the concentration of a solution of CoCl2. So you have 65 grams of CoCl2. We know that it's about 130 grams per every 1 mole. That's going to give us 0.5 moles of CoCl2 divided by the volume, which is going to be 0.25 liters. Remember that there's 1,000 milliliters in every 1 liter.